partial of f with respect to y would be x cubed plus 2xy minus e to the y. I like it. See, there's none of that weird, where does y prime go? None of that. Let me put this up here. So then dy dx would be negative fx. So negative 3x squared y plus y squared. Oops. So that'd be minus. Is that cool? Negative what we got, partial is x, over what we got, partial with y. And if you guys realize, those are the same thing, just with the negative sign put on the top. So it's just a different way to do implicit. But now we can extend this same idea to a function of 3 variables, sort of, right? This is almost a function of 2 variables, but since it's equal to 0, it's not really. But I can look at it as if it is and apply the same rules. So now we can do this. If I have big ass f of xyz equals 0. Then I can say like this. 0 would be partial of f with respect to x dx dx plus partial of f with respect to y dy dx plus partial of f with respect to z become a dz dx. This is 1. Oh, I'm not being careful. All right. Now I've got to be a little more careful than I'm actually being. X is implicitly a function of y and z. Y is implicitly a function of x and z. Z is implicitly a function of x and y. So these should actually be partials. And the reason that's important, well, it's important for just because it should be there for correctness. But when I do d by dx, what's y? When I take the derivative with respect to x partially, what do I consider y to be? A constant. So what would partial of y with respect to x be? 0. So what do I end up with? I end up with 0 equals d partial of f with respect to x plus partial of f with respect to z dz dx. And now I can solve for dz dx or df dx. Freakiness. Or whatever I want. So in this case, I actually want dz dx. So it would be negative fx over fz. Now I can do the same thing with respect to y, like we did earlier with respect to s, with respect to t. I did this with respect to x. We could do the whole thing again with respect to y. Yes, sir?
How does that become 0?
Because when I do this to something, I'm assuming y is constant. So then what would the derivative of y be? 0. So now if I do this whole thing again,
X, then it would be...
if I did this whole thing again with dy, which is what I would do next, dy, this would be 1 and this would be 0.
But if y is a function of x, then it doesn't just go 0. And or if you're going to do that, then why didn't you do it with z?
So this is the one, this is my method. Z is assumed to be a function of x and y. Because that's where this would have come from, right? If I had like z equals x squared minus y or something, I could pull us all over, figure out what big ass f is. Okay. So z is a function of x and y. I think I mixed it up when I said that earlier. Yeah. So x and y are my independent variables.
Yep.
Z is the one that depends on those two. I like it. So you get a similar thing for dz, dy. Remarkably enough, which you might expect. You do the whole thing over again, but with respect to y. So with that, you can do stuff like, oh, let's see, did they give me a, did they even give me there? There it is. Yeah, so anytime you step up the number of parameters, so in this case we are looking at x and y as if they were parameters. So we're doing exactly the same stuff we were doing when I was looking at s and t. We're doing it exactly the same way, just looking at x and y themselves as if they were parameters. So we can do, so they're going to give me some function like this, and they're going to ask me, well, what's dz dx? And I can figure it out using this. Like, yes?
Are those partials there as well? The dz dx and dz dy?
No, definitely not. They're totals. Which is why, alright, I really want you to understand why we had to go through this. This, if that was my function here, c equals x squared minus y, this is an easy question. Easy question. What is this going to be if that's my function?
2x.
Yeah, 2x, because y is a constant. This is not the same idea. This is the total derivative with respect to x. It's not a partial with respect to x. I'm not assuming anything as a constant. That's the difference. So to get this, I could do this. So let's see what that is, and let's see how it compares, and then we'll probably call it a day. What is fx? Well, first off, with this function, what is big ass f? All you have to do is what? You choose a place. I could subtract z over, right? I just needed to equal 0. Doesn't matter if you pull those over, pull that over, the negatives would cancel out eventually, you'd end up in the same place. So I'm going to do this. So to do this, what's fx? 2x. What's fz? Negative 1. So dz dx is 2x. Like, same thing you would have gotten this way. But now you can do, if you have stuff like, so that's a nice example that it gives you the same idea as before, but now you can do stuff like when you have mixtures of things going on. So it's like implicit differentiation taken into the third dimension. So when you have these mixtures going on, you can't solve for z. There is no way to really get at this directly. I need some help. All right. More email. All right, so we made it up through 14.5. I haven't given you guys your practice test yet. Let me do that real quick. Doesn't bother me about that. By the way, everybody who's still here, this is what's bugging me. There should be partials there. Because you're doing it, it's still the same idea. Z is a function of x and y, so you gotta do partial x, partial y. That was bugging me in the back of my brain. Thank you.
And I have partial. And here it is that this